Now for some really cool stuff. Section 211 is on Schauder basis. In the book, there's only a couple sections long. We'll go into more detail in these topics and some of the supplemental material. Some of it's covered in section 5.1, groups, fields, and vector spaces of a graduate real analysis book with some applications and some topics on wavelets that I was a co-author on some years ago. But what we're going to look at is two ideas for a basis of a normed linear space. One much more pragmatic than the other. And first, a Schauder basis is what you might expect it to be in an infinite dimensional normed linear space. A sequence, x sub n, and a normed linear space, x, capital X, is a Schauder basis if for every x, a vector in the normed linear space, there's a unique collection of scalars, alpha sub n, from the field, usually the reals or the complex numbers, where x can be written as uniquely, so uniqueness plays a role in getting us some kind of concept of linear independence. Every x can be written in the form sum from 1 to infinity, alpha sub n, x sub n, where the alpha sub n's are simply the coefficients. So this is awfully similar to the definition you have for basis in sophomore linear algebra, with a simple exception that you're taking a series. You're writing these x vectors in terms of series instead of finite linear combinations. Is that going to make any sense? Yeah, we're in a normed linear space, so we have a norm, we have a metric, and we can talk about limits. So we can talk about limits of sequences of partial sums in particular, and this actually makes sense that this series would converge to element x. So it's meaningful. In an arbitrary linear space, it isn't. Without the norm, then you don't have a way to measure distance, so you can't talk limits, and therefore you can't talk series. So Schauder basis, that's a good kind of basis, the topic of this section, though there are other kinds of bases. In straight up linear algebra, as a definition and a note sort of combined, we require that every element of a vector be written as a finite linear combination of basis vectors in a unique way, the uniqueness giving, again, the linear independence. So the difference in a Schauder basis and the kind of basis you talk about in sophomore linear algebra is there's none of this. There's no series. You don't talk about series in linear algebra in this sense, unless you do some somewhat advanced stuff. So if this is the case and you insist on finding a collection of vectors for which every vector can be written as a finite linear combination of elements, such a basis is called a Hamel basis. I don't think Promislow even mentions this in his book, but Hamel basis is the kind of thing you deal with in linear algebra. And you're used to finding a Hamel basis for Rn. It's the usual standard basis. It's a little finite set. Yeah, things are nice in finite dimensions. You get into infinite dimensions and things become more complicated. And I recommend you settle yourself for a Schauder basis in these infinite dimensional spaces. Do Hamel bases even exist in infinite dimensions? Does every vector space have a basis? Because the definition of vector space doesn't say anything about a basis of that vector space. You never had a problem in linear algebra. In linear algebra, you were always an Rn or possibly Cn. In fact, every vector space does have a Hamel basis. They're impractical to find, but they do exist. You use something equivalent to the axiom of choice to show that every vector space has a Hamel basis. So basis isn't part of the definition of a vector space, but every vector space has a basis in the sense of Hamel. That is, in the sense of writing vectors as finite linear combinations. The buzzword in all of this is impractical. In infinite dimensional space is such a thing as impractical. You want a Schauder basis if you're in an infinite dimensional normed linear space. But FYI, these are involved deep ideas that you don't discuss probably in sophomore linear algebra, but every vector space does have a basis. It takes the axiom of choice to establish that. That means it's way impractical to find one. A little story about Banach spaces and bases. Stefan Banach, the Banach space chap, conjectured in 1932 that every separable Banach space has a Schauder basis. Remember, a separable Banach space was one that has a countable dense subset. So Banach conjectures, separable Banach space, that Banach space has a Schauder basis. But a counterexample to this conjecture was found in 1973 by Per Inflo, a feat for which he was awarded a live goose by Stanislav Mazur, the only history of math story I know that features a live goose. There's a link to some historical records that document this. I think it's a common story that's told, but apparently well documented. Banach's conjecture appears in 1932. There's an English translation of it. Inflo's solution from 1973 appears in Acta Mathematica. Project Euclid has a copy of Inflo's paper posted out there, and there's a link to it in these online notes. So this is unfortunate. Such a thing won't happen, it turns out, in Hilbert spaces, complete inner product spaces, yet to be addressed. So what I read into this is Banach spaces can have some difficult and surprising properties. Banach spaces can behave in exotic ways. Hilbert space won't behave like this. If a Hilbert space is separable, if a Hilbert space has a countable dense subset, then that Hilbert space will have a Schauder basis. And that's really the closing comment here. Every Hilbert space, every separable Hilbert space has a Schauder basis. In fact, it turns out every infinite dimensional separable Hilbert space is isomorphic to the space little L2, square summable sequences. We encountered the little LP spaces a couple sections ago. So just as you can classify a finite dimensional vector space with scalar field F is isomorphic to Fn. If the field is the real numbers, it's isomorphic to Rn. And an infinite dimensional vector space, well, with a few other details thrown in, is uniquely determined by its dimension. An infinite dimensional vector space, properly stated, an infinite dimensional separable Hilbert space is isomorphic to L2. And I'll refer to these in some of the supplements as the fundamental theorem of finite dimensional vector spaces and the fundamental theorem of infinite dimensional vector spaces. You classify finite dimensional vector spaces in linear algebra. We'll classify infinite dimensional vector spaces. Yeah, with a few extra bells and whistles to allow us to get that classification. And that takes care of 211. Probably we'll step aside now and look at some of that supplemental material I mentioned earlier and go a bit more in depth into some of the claims that were made in Promislow's book in this section. So I will see you in supplemental material. Have a nice day.